I like number one. I like number one. I like number one. This is fair game. You're going to see something like this on your test, except I will tell you on the written section of the test, I will also give you a picture. So this is just slightly tougher because I did not give you a lovely picture, unlike, say, example 2. So example 1 says this. A 12-kilogram curling stone, I'll call this mass C for curling stone. Hits a stationary bucket of sand, I'll call this mass B for bucket. After the collision, the curling stone's velocity is 4 meters per second east, and the bucket has a velocity of 4.3 meters per second at 23 degrees east of south. I see directions. I'm going to draw compass rose because it's not like I've ever botched that before. What was the initial velocity? Okay. Luke, my friend, is there a collision? Okay. That means this is a job for... You're right, someone said it here. Someone said the word conservation. Conservation of what? There's going to be momentum. So I'm going to say the sum, the total, the amount of momentum before equals the amount of momentum after. And I'm already recognizing I see angles and stuff. I'm going to be drawing things tip to tail. I'm going to be getting tricky with it. I'm going to be doing the whole schmear. Luke, before the collision, what was moving? Mass C, mass B, both or neither before the collision? So I'm going to have the momentum of object C incoming, initial. What does the equal sign actually stand for? Wham! They collide. That's what it stands for. Okay? After the collision, what's moving, Derek? Mass C, mass B, both or neither? Stuck together or separate? Separate. Now, in your homework, if you start taking some shortcuts, I won't freak out. In fact, on the next one, I'll show you how I would do these in my homework. These are tough enough, though, on a test. I go very, very systematically because now, can I go like this? Mass 1, V1, mass 2. Can I do that and just get the V by itself? No, I got angles. So what am I going to do? Dolp. I'm going to draw a little picture. Luke, what does the incoming velocity of the curling stone look like? It's a trick question. It's a trick question. What does it look like? They didn't tell me any hints. That's why this is a tricky question. Look, what does it want me to find?
Initial velocity.
Of the? Because I don't know it. Now, if they had given me a picture, I could at least draw a fake arrow and know that the arrow looked kind of right, which is what makes example 2, the next one, a little easier than this. They didn't give me a picture. Okay. Wham, they collide. Luke, my friend, what does the final direction and velocity and momentum of the curling stone look like?
4 meters a second
East, you say? Now, I'm not going to put a 4 on here. What's going to go on that line is the momentum. You might even be able to do it in your head. Yeah. Plus, what's the momentum of the bucket after the collision? Can you read to me, starting with the 23, the direction?
23 degrees east of south.
East of what?
South.
East of what? Okay, this is a little weird. I'm going to start out going south first. What of south? Which is going to be to the right. How many degrees? 23 degrees. How long is this arrow going to be? More specific, please, exactly as a number.
4.3 meters.
It's not. Don't ever put velocities on these. Velocity is not conserved. Momentum is what's conserved. And that's a common mistake. Kids start putting velocities and they think, oh, that's all I need to... No, it's mass times velocity. It's going to be 8 times 4.3. I can do that in my head. It's going to be 32 plus 2.4. Is the answer 34.4? You should have been able to do it in your head as well, Luke, my friend. Now, from lesson 3, a couple lessons ago, the reason number 1, the first question, was so tough, there I gave you this vector, I didn't tell you anything about this vector. Here, even though I don't know anything about this vector, I do know the two vectors that I'm adding together, and how will I add them together? Draw them. So you ready? It's going to look like this. I'm going to go 48, and then 34.4. As a picture, I'm pretty sure that that bottom arrow there is what the curling stone came in at. And once you've drawn that triangle, put your pencil down for a second and look up. Ready, Luke? How big is this angle right here? So you're saying if I take that 34.4 and I draw a vertical line, this angle, how big? Don't write this down. I'm going to muck up my diagram. So you're saying if I take a vertical line, how big is this angle right there? You agree with that? How big is this angle right here? 90? So now you can pick your pencil up and I can say, all right, how big is that angle? How can you calculate it? More specific. Add what? 113, right? 113, I think? 90 plus 23. So 113? Okay. So here is one more little bit of, I have to do a tiny bit of cleverness to find the mystery angle. Right angle, SOHCAHTOA trick? No. In fact, I think this is going to be cosine law. I don't have a pair. By the way, you've noticed the cosine law also occurs when you have two sides and the angle that's connecting them, and that happens in most of your momentum questions. It won't happen in all of them. Sometimes you'll be able to use the sine law. When will you be able to use the sine law? Honestly, if, Shayna, they give you one of those angles in the picture. I think on your take-home quiz, there's one question where I give you the extra angle, and I did that just to shorten it a little bit, and you can go straight to using the sine law to find missing stuff. Oh, the cosine law still works. Speaking of cosine law, I think then we're going to say this. Mystery momentum initial squared equals 48 squared plus 34.4 squared minus 2 times 48 times 34.4 cos 113. And then remember, this gives you a squared, so when you're done, square root. The final momentum initial, I'm going to get 48 squared plus 34.4 squared minus 2 times 48 times 34.4 cos 113. Wow. Oh, square root. I always forget to do that. You get 69.121? Which, of course, Luke, is not what they asked me to find. What did they ask me to find? Now, how could I give you this question but shorten it and turn it into a multiple choice question? I might just say, find the magnitude of the initial momentum. You could quit here. You would have done most of the trig and most of the physics. Or I could just say, find the direction of the initial momentum. You would find this, and you could go straight to the sine law and not bother finding the velocity. But here, they want the whole thing, the initial velocity, magnitude, and direction. Okay, if I know momentum, how do I find velocity? Divide by the mass. So it's going to be 69.121 divided by, was the mass 12? And I get 5.76 meters per second. Now, if I had said, Jess, find the speed, you could quit, because that's a speed. Doesn't need the direction. That would be another way on a multiple choice to kind of shorten the question and still have you do most of the physics. Did I say, Luke, find the speed? Okay, at. Which theta am I going to find? It's always where my vector is coming from, where it's originating from, there. By the way, that theta, north of south, east of west, what of what? South of east or east of south? East of south would be if it was that one, right? If it was this one down here. South of east is this one. So you're right, south of east. South of east. Now let's find theta. How am I going to find theta? Sine law, because now I do have a pair. It's going to be the sine of theta divided by 34.4, what's across from it, equals the sine of the angle that I know divided by what's across from it, which I didn't know before, but I now know is 69.121. I'll be honest, what I often do is rather than use the 69.121, this 5.76 came from dividing by 12. I'll often multiply by the mass, and then I have the answer button back on my calculator with all of the sig figs. It actually ends up usually being less typing than typing in the longer decimal anyhow. Luke, how will I get the sine theta by itself?
Times over 34.5.
And I'm going to use my answer button. And that, what? Oh, that's the sine of theta. Shift sine of 0.458115, that. And I get 27.3 degrees. That question is absolutely fair game for the written section of your test, although I'll give you a diagram. Okay. Then we started combining both energy and momentum, like the next one, example 2. Example 2 says, oh, they gave me a picture. You know what? Hannah, since they gave me a picture, let's see if you and I, if we can take some shortcuts. Now, I wouldn't do this on a test, but we're in our notes and our homework. Let's see if we can. What does part A want us to find? And direction of the? Which one? Okay. Is there a collision? Yeah. Are there angles? Okay. You know what? Since there's angles, I'm going to do north, east, south, west. Except for some reason I put the south way over here, or I put the east in the wrong place, really. There we go. Is there a collision? You said yes. So that's a job for conservation momentum. I'm going to skip this step, but on a test I would write the sum of all P initial equals the sum of P final. Vector, vector. Let's call this mass 1. Let's call this mass 2, because it works. Before the collision, what's moving? Mass 1, mass 2, both, or neither? After the collision, stuck together or separate? Let's see if we can go straight to drawing the arrows. So the initial momentum of mass 1 looks from the picture like that. How long is it? I knew you could do it in your head. Bam! They collide. After, it looks like I have one going that way. And I think, Hannah, that's the mystery momentum, because they have a V there, so I don't know its momentum. I just know it went that way. And then it looks like down this way with a little 10-degree angle right there. I'm even going to bet, really, you couldn't go 6.7 times 2 in your head? Really? Please tell me you got 13.4. Wow. So we skipped a couple of written steps just to see if we could, but I think we're good so far. Even though the difference between, Luke, your question that we did and the one Hannah and I are doing is we didn't know any of these. The fact that I know roughly what this looks like lets me draw the triangle. How do I want to add these together? And here's what's important. I know that when I add them tip to tail, I'm going to get a nice horizontal line of 16. So it's going to look something like this. Mystery momentum, 13.4, 16. By the way, this is terrible scale. I think the triangle would more accurately look like this. Because, Hannah, 13.4 and 16 really aren't that far apart, I think these two should almost be the same length. I'll bet you in real life it kind of does this, and then you have that, where the two long sides are nearly the same length. And I've drawn my standard. You notice I tend to almost draw an isosceles kind of flat triangle, kind of a one-size-fits-all. And it'll work. Just saying, my answers might look funny if I try to put them in my triangle to scale. Oh, how big was this angle right there? Doesn't help me. Or does it? And once again, oh, I have two sides and the angle between them. You know what? This is going to be a cosine law question. Okay. I think I can go like this. Mystery momentum of 2 squared equals 16 squared plus 13.4 squared minus 2. 16. 13.4 cos 10. And then square root. I'm going to get the momentum of object 2 is going to be 16 squared plus 13.4 squared minus 2 times 16 times 3.4, Mr. Duick? 13.4 cos 10. Wow. Oh, square root. I get 3.6434. Yes? Hannah, did the question say find the magnitude of the momentum for part A? Did it say momentum? I have momentum. How can I change this into a velocity if I know the momentum? Without your calculator, in your head, you're going to look at mass 2, which is 10 kilograms, and in your head, without your calculator, please God, you're going to divide 3.6434 by 10. I knew you could do that. Now that's the speed. They said velocity, so I have to add a direction. I guess the theta that I want is that one there. So it's going to be sine of the mystery angle theta over what's across from it equals sine of 10 degrees over 3.6434. Although I'm going to use my answer button, and conveniently, because I did the math in my head, I actually still have this stored on my answer button. See, wasn't that nice? 13.4 sine 10. By the way, on a test, would I still probably, even the 2 times thing that I teased you about, would I still type it on a test? Almost certainly, because Lord knows I've made dumb mistakes and I can avoid those on a test. But you've had me long enough to know I'm always trying to push the envelope in the homework. How good can I get at this stuff? Divided by answer button and then shift sine of that. I think we're going to get a fair-sized angle. 39.7 degrees. North of south, east of west, what of what? Yeah. By the way, that's the answer to part A. Mateo, what did part B want me to find? You know what? kinetic energy lost is going to be what you started with minus what you ended with. Kinetic energy initial. By the way, look up for a second, folks. Technically, you could even write it this way. The total kinetic energy we started with minus the total kinetic energy we finished with. You could bring in the sum of and use it there as a little handy-dandy shortcut, too. That's really what we're saying. What was moving before the collision? Mass 1, mass 2, or both? Mass 1. So I'm going to have a half. What was mass 1? How big? 2. What was its initial speed squared? And its speed, I don't care about direction. 8 squared. That's how much energy kinetic energy we started with. And then after, what was moving? Both? Okay, so I'll put that in brackets, both. I have 0.5 times 2. How fast was the 2 kilogram mass moving after? Hello? 6.7, is that what it says? Squared. And I have a half times 10 times 0.364 squared. What I started with, take away what I ended with. Whatever's missing is what I lost. Now, in the textbook, another way to phrase this would be to say, find the work done during the collision, but if you were solving it in terms of work, instead of going initial minus final, because work is the change in, you would go final minus initial. You'd get the same magnitude, but you get a negative answer, and what that's telling you is you lost energy during the collision. Here, because I said find the energy lost, the word lost itself has the negative implied, so we won't get a negative answer, because a negative loss would imply a gain. We didn't gain energy. I'm going from memory. Do you get something in the 18s or something like that? Or am I totally wrong? 18.4 or 5? 4.6? Did you use rounded off values or did you use your answer button? Okay, I'd probably take both. Anyways, the KE lost is around 18.4, 18.5 joules. And again, this is not violating the law of conservation of energy. Total energy is always conserved. Total momentum is always conserved. But kinetic energy, which is a subgroup of energy, is rarely conserved. It's only conserved in a perfectly elastic collision. By the way, in fact, you lose the most kinetic energy in an inelastic collision. That's where more energy is turned into heat and stuff like that. Turn the page. I see part A, velocity, part B, find the kinetic energy lost. I see one object moving at angles, 15 degrees north of east. I see another speed due east. I think it's very similar to the one we just did. I like example 4. I like example 4. I like example 4. Example 4 is a nice question. Read along with me. A metal disc explodes, boom, into 3 pieces, which fly off in the same geometric plane. That's my way of saying they fly off staying flat. We don't want to bring a y component into this. The first piece has a mass of 3.4 kilograms. It flies off north. You know what? I see a compass coming up here. At 11 meters per second. The second piece has a mass of 4 kilograms. It flies east at 13.5. What's the speed and direction of the third piece, which has a mass of 2.4 kilograms? By the way, this is the beginnings of bomb forensics, if you're wondering. Okay? We'll talk about how some of this is used today. Now, I have to water the question down. In real life, a bomb would blow up into thousands of fragments, and you would use software. You would collect as many of them as you could, you would measure their masses, and you would use software to kind of reverse engineer this. With 3 fragments, we can do this by hand. Jilun, Is there a collision? Say no.
No.
Is there an explosion?
Yes.
In other words, is there a jeune? This is a job for conservation of momentum. For an explosion or a collision, you want conservation of momentum. So I'm going to start out by writing the sum of all the momentum before equals the sum of all the momentum after. I'm going to call the first mass mass 1, second mass mass 2, the third mass mass 3, because that's how they refer to them. Gilun, before the bomb explodes, what's moving? Mass 1, mass 2, mass 3, or neither?
Mass 2 and mass 1.
Before the bomb explodes?
Uh,
What's moving before the bomb explodes? It's a trick question. Nothing. In fact, stop. What's the momentum of the bomb before it explodes if nothing is moving?
Zero.
Ah! This is kind of why explosions are neat. Here, the equal sign does not mean wham, they collide. Here, the equal sign means boom, they explode. Right? Gilun, after the explosion, what's moving? Piece 1, piece 2, piece 3, or all of them?
All of them.
Stuck together or separate? I think we can safely say in a bomb, always separate.
Yeah.
So we're going to have this momentum of the first piece as a vector, momentum of the second piece as a vector, momentum of the third piece as a vector. The fact, Gilun, that I see, look up, north and I see east, there's angles, different directions. So I'm going to dulp. Piece 1, what direction did it fly?
North.
So that's going to be an arrow pointing straight up. What am I going to put on that arrow? 11 times 3.4. I can do my 11 times table in my head. It's going to be, well, if it was 11 times 34, it would be 37.4. Double check me. I've showed you all the 11 times table trick, right? No? Put your pencils down, look up. You ready? And I'm not talking about the wishy-washy 11 times trick. I mean, yeah, 11 times 8 is 88. That's wishy-washy. I mean, for two-digit numbers. You guys all know that 11 times 23 is 253. It is, I'm right. Or 11 times 61 is 671, because it is, I'm right. Or you all know that 11 times 32 is 352. I'm right. Have you spotted the pattern yet? Yes? Okay, so what would 11 times 41 be? First digit, last digit, the middle, you add them up. It gets a bit trickier when you have to carry a 1. If you go 11 times 78, last digit is an 8. First digit should be a 7, but what's 7 plus 8? 15. I got to carry a 1. Instead of a 7, I got to put an 8 there. Okay. They don't show you that? Gosh, what are they teaching you all in high school? So, I went 11 times 34, 374, and then I just moved the decimal point back 1 because it was 3.4. See, I'm not that smart. I just have more tricks up my sleeve. Plus, Gilun, mass 2, what direction was it moving?
East.
It's going to be 4 times 13.5. Timesing by 4, that's the same as going times by 2 twice. So 13.5 doubled is 27. Doubled, check me out, but it should be 54. Plus, Gilun, do I know the direction of the third piece?
No.
Question mark. Okay. Ah, but do I know 2 of them?
Yes.
And they're vectors with plus signs? I can add them. How would I add them? Draw them. So you ready? Here's why I like this. This is kind of neat. There's some lovely physics and some lovely thinking here. So as a vector diagram, it's going to look like this. 37.4. And then 54 would be a little longer, about like that. Here's the key. What was the momentum of the bomb before the explosion? 0. So what must the momentum of the bomb be after the explosion? So what will this vector triangle add to? 0. How would I show that? If this was a displacement, what would 0 displacement be? I would end up back where I started. This is momentum. What will 0 momentum be? I will end up back where the final vector is that. That is the third object. Oh, and ready? It's a right angle, which means Pythagoras and SOHCAHTOA trig are back in play. In fact, I can find this with Pythagoras. So in real life, if you're a forensic investigator for like the RCMP or FBI or whatever, you would be piecing together thousands of little mini vectors. Now, there would be some pieces that would have really disintegrated, you couldn't find. You would probably have done enough experiments that you could take into account roughly what percentage of the pieces you were missing and still come back with a pretty accurate guess. P3 squared equals 37.4 squared plus 54 squared minus 2 times 37.4 times 54 cos 90. Mr. Dewick, you don't need to do the cosine law. I don't, but it turns out the cosine law still works. Do you know why? What's the cosine of 90 degrees? What's the cosine of 90 degrees? 0, which means all of that vanishes. Pythagoras is actually a special subcase of the cosine law when the cosine theta, when theta is 90. So it's going to be 37.4 squared plus 54 squared equals square root. There's the magnitude of the momentum, 65.6868. I can remember that. Momentum is 65.6868. However, Gilles, that's not what they asked me to find. They wanted me to find the velocity. How can I find the velocity if I know the momentum? What was, I've scrolled down, what was the mass of object 3? So it's going to be 65.6868 divided by 2.4. And I get a speed of 27.4 meters per second. To make it a velocity, I need a direction. At. And the direction is always where my vector is originating from, which in this case is the top right corner. I could use the sine law. I could go sine theta over 37.4 equals sine 90 over P3. But you know what? Are we in a right triangle? I think I can go SOHCAHTOA. Which trig function? Equals opposite over adjacent. Shift tan of opposite over adjacent. And I get 34.7 degrees. What of what? North of south, east of west, what of what? North of south, east of west, what of what? This is going to be, it's south and west. Is it west of south? South? This is south of west, right? Before we go on, Gilles, do you know how fast this is traveling? Say yes.
Yes.
Do you know its mass?
Yes.
Could you find its kinetic energy then? Say yes.
Yes.
Could you find the kinetic energy of this guy? Yeah. Could you find the kinetic energy of this guy? Yeah. That would tell you the kinetic energy of your bomb. And so if you're a forensics investigator, you would know the mass and how much energy from that. You could probably figure out what the bomb was made out of. pretty accurately. Oh, is it C4? Was it what type of explosive? They would have charts and data, but they would know roughly how many joules per kilogram of different explosives. And again, there'd be some guesswork because you would never recover every single piece, but it would start like this with the physics. Yeah. It's always where the vector is originating from. So here's my vector, never where it's pointing to, always where it's coming from, always where its tail is starting. Okay? Always. So that's worth committing to memory or doing. Yep. Okay. But then I apologize. This is kind of morbid in this day and age. But for what it's worth, here is some forensics for bomb investigations, physics. In real life, much more complicated, but the physics would start here. Example 5. I like this question, I like this question, I like this question. We did do one like this in lesson 4 where we had a roller coaster come down a hill. In fact, it was the question where you had such wonderful artwork. Remember that one? Such beautiful drawings, Mr. Dewitt. Well, thank you. I'm all embarrassed now. Since we've done one like that, I'm going to gamble and say that you're okay. And instead, I'm going to say, I'm not going to do the scholarship question. Your homework is you can start every question now on the ultimate momentum review is fair game.